Welcome to the course on an introduction to information theory. I am Adrish Banerjee. So in this lecture we will continue our discussion on block to block length coding of a discrete memoryless source. In the last lecture we described what we mean by typical sequence, and we showed some properties of typical sequence which are collectively known as asymptotic equipartition property. In this lecture we are going to see the consequence of those asymptotic equipartition property. What is the consequence of them for block to block length coding? So we will first quickly refresh our asymptotic equipartition property and its consequence, and then we will talk about block to block length coding. Now remember, when we are talking about block to block length coding, it's a lossy compression because we have large blocks of data which we are mapping into small blocks of data. However, since given a source distribution, we know not all sources are equally likely to happen. Some sources are which we showed are typical sequence which are likely to come out of a particular source. We will try to encode those sources using unique code words, whereas the sequences which are not likely to happen, the non-typical sequence, we are not going to assign a unique code word to them, and hence we will get some lossy compression. So just quickly go over the three properties of asymptotic equipartition property. So the third property says that number of epsilon typical sequence is given by 2 raised to power L into h of u, and property 1 says that each of these typical sequence happens with probability 2 raised to power minus L h of u, and the third property says that total probability of these typical sequences is nearly 1, which means that if you take large enough L, most of the time the sequences that will come out of this source are likely to be typical sequence. And as we said, these three properties are collectively known as asymptotic equipartition property. So let us see now how we can use these properties to design our block to block length encoder. So let x1, x2, xn be independent IID distributed random variables drawn according to some probability mass function p of x. Now we are interested in short description of these xi's, right? So let us divide this set of sequences into two sequences, one which is typical sequence and other one which is a complement of the typical sequence. Now how many typical sequence exist? That is block length 2 raised to power block length h of u, right? So to represent uniquely each of the sequences in the typical set, we would require nh plus epsilon plus 1 bits, right? Because we know the number of typical sequence, if you have block length of L, it's 2 raised to power L into h of u. So to uniquely define each of these typical sequence using a code word, we would require these many number of bits. And obviously the non-typical set cannot be more than n log cardinality of x plus 1. Now we can prefix the typical set by 0 and non-typical set by 1. So essentially we are increasing the block length by 1. So we are going to use n into h plus epsilon plus 2 bits to describe code words which belong to typical sequences, and we are going to use n log cardinality of x plus 2 bits to represent non-sequences which are coming out of non-typical set. Now clearly this code which I designed so far is one-to-one and is easily decodable. Why? Because each of the typical sets I have assigned one unique code word, and so far I have done the same thing for non-typical set as well, because I am using this many number of bits. And as we said, typical sequence will typically require block length into h of u number of bits to represent it. So let us compute the expected code word length. Now the expected code word length can be written as sum over all the sequences of length n, probability of occurrence of those sequences multiplied by length of those sequences. Now we have partitioned our set of sequences into two, one corresponding to typical set, another the complement of typical set. So this particular term that you see here corresponds to sequences that belongs to typical set, and this summation corresponds to sequences that belongs to non-typical set. Now, so what is the length required to describe a typical set? Now I was using n times h plus epsilon plus 1 bits to represent a typical set, and remember I was prefixing it by a 0. So I am totally using n into h plus epsilon plus 2 bits to describe these code words corresponds to typical set. Similarly, for the non-typical set I was using n log of cardinality of x plus 1, and I was prefixing it by 1 to denote that it belongs to non-typical set. So the length of these code words belonging to non-typical sequences is given by n log of cardinality of x plus 2. Now what is this probability? This probability is basically probability of occurrence of typical set, and this is the probability of occurrence of sequence being not a typical set. Now we know from asymptotic equipartition probability that this probability is very small, some epsilon or something like that, and this probability is close to 1. So I can then, this probability then can be upper bounded if I consider this to be 1, and this I consider this probability to be epsilon. I can then upper bound this probability by n times h plus epsilon plus 2, and this is epsilon times n log of cardinality of 2. This is much larger than 2, so just writing it this way. Okay. Now this can be written as n times h plus epsilon dash, where epsilon dash is given by this quantity. Okay. So this is expected code word length if I use the scheme which I just described. Now epsilon is small, so you can see, and n is large, so this epsilon dash is very small. So roughly I am using close to n times entropy of this source. Now let us state the block to block length coding for theorem for the discrete memoryless source. So we are given a Chiari discrete memoryless source whose output entropy is given by h of u, and we are given two positive number epsilon 1 and epsilon 2, they are small. Then for large L there exists a Chiari block length of code n for all those messages of block L such that n by L is less than equal to entropy of u by log d plus epsilon 1, such that probability that the code word will not be uniquely decodable, like probability that the code word will not be uniquely specify the message, a probability of error basically, that is also upper bounded by epsilon 2. So what are we talking about here? So we have an input of block length L and we are coding it into output sequence of block N. So clearly N is less than L, then only we will get compression. Now what should be N by L? So this says the relation between N by L. If we take N by L to be less than equal to HU by log D plus small epsilon, then probability of basically being error, probability of failure is upper bounded by some epsilon. Now we will show the converse also, that this ratio N by L cannot be very small, cannot be very small, because if this ratio is very small, then we will show this probability of error, basically a failure, that increases, that will show subsequently. So let us show this result. So suppose we are assigning a unique DRE code word of length L to each of the M typical sequences, but we use only a single additional code word to code all non-typical sequences. So there are total M typical sequences, we are uniquely defining those M typical sequence by a code word. However, for all non-typical sequences we are using only one code word. In other words, if we transmit a non-typical sequence, then the receiver will not be able to make out what was the sequence received, but if we transmit a typical sequence, the decoder will be able to exactly find out what sequence was transmitted. And remember, from the AEP property we know that if L is large, most of the sequences generated by the source are going to be typical sequence. So for typical sequence we are assigning a unique code word, whereas for all this set of non-typical sequence we are just using one code word. So then number of code words we require is M plus 1, M for M typical sequence and 1 for all non-typical sequence. So the smallest n that satisfies this condition, because we are using a DRE code word, so smallest n that would satisfy this condition is given by this. So the n should be such that M plus 1 is greater than d raised power n minus 1 and it is less than equal to d raised power n. So further, simplifying it, I am just writing M is greater than d raised power n minus 1, or d minus, take a log, d minus n log of d is less than equal to log of m. And what is m? M is upper bounded by 2 raised power 1 plus epsilon L times h of u. So if I take log of that, I get this expression, right? Now simplifying further, I can write this relationship in this particular fashion. So n by L is less than equal to HU by log D plus epsilon h of u by log D plus 1 by L. Remember, we are talking about epsilon when epsilon is very small, close to 0. We are talking about L, which is very large. Okay, so when epsilon is small, this term will be close to 0. When L is large, this term is close to 0. So we can then write this as n by L less than equal to h of u log of d plus epsilon 1. And remember, since most of the sequences are typical sequence, so probability of error is going to be small, is less than some epsilon. From the property 2 of typical sequence, we know the total probability of epsilon typical sequence is close to 1. So that will then prove this result, that if you have a k-array discrete memoryless source whose output entropy is given by h of u, then there exists a d-array block code of length L for message sets of length L such that n by L is less than equal to hu by log d plus epsilon 1, and this while ensuring that probability of basically making a mistake is also bounded. Now the next question to ask is, can we make this n by L ratio very small? What is the consequence of that? Because this says n by L is less than equal to hu log d plus epsilon. Can I make n by L very small? The answer to this will come in the next slide, where we will show what happens. So we cannot make n by L very small without increasing our probability of failure. So we are going to show that next. So we are going to show for a discrete memoryless source, so given positive number epsilon 1, epsilon 2, there exists a source coding scheme such that n by L is less than this, and probability of failure basically where we do not estimate our bits, source bits correctly, is bounded by epsilon. So this is the kind of block diagram that we are looking at. We have a discrete memoryless source which is spitting out these UIs. Now these UIs are k-array alphabet, right? So each of these UIs can take k different values. This has been fed to a, and my input block length is L. This has been fed to a block source encoder which takes these blocks of L bits and transforms into block of length N, and these code words are d-array code words. Now once I have this code word at the receiver, essentially I need to reconstruct and get back my original sequence. So u1 hat, u2 hat, ul hat is the estimate of the source bits which were encoded using this block to block length encoder. Now as I said, we cannot make this ratio n by L very small. So we are going to now quantify in terms of probability of error. So we define this average probability of error in this particular fashion, where probability of error at the ith bit is defined like this. So if ui is not same as ui hat, that is defined as probability of error at the ith bit. And if we take the average of error over all L bits divide by L, that's going to give us our average probability of error. Now this average probability of error is less than this probability of failure. So probability of error is upper bounded by probability of f, and this we have derived in the previous lecture, that this depends on k, this depends on block length L, this depends on epsilon square, this depends on p min probability of u. And since this is small, average probability of error is also bounded. Now as I said, we are going to ask the converse. So in other words, we are going to ask, can we make probability of average probability error very, very small if we make this ratio also very small? So the answer lies here. So here we cannot make ratio n by L much smaller. You can see from this relation, if we make this n by L ratio smaller and smaller, then probability of error is bounded from below by a larger quantity. So we cannot make this n by L ratio much smaller without increasing the average probability of error. So we are going to prove now that the average probability of error is related to number of bits that we use to encode our block of data of length L. So binary entropy function was using capital H notation. Binary entropy function of this average probability of error plus probability of error log of k minus 1 is upper bounded by uncertainty in u divided by log d minus n by L whole multiplied by log of d. So let us prove this. So before we prove this, I just want you to again go back and look at the block diagram, this block diagram. So we are using UIs to denote our output of a discrete memoryless source. We are using UI hat to denote the estimate of these UIs, and we are using XI to denote our source encoded bits. So you can clearly see UX and U hat, they form a Markov chain, right? So we can make use of data processing lemma. So let's proceed with the proof of this. So this relates the average probability of error to number of bits used to encode in the case of block to block length coding. Now from the definition of mutual information, we can write the mutual information between u1, u2, un and x1, x2, xn as uncertainty in x1, x2, xn minus uncertainty in x1, x2, xn given u1, u2, un. And we know for discrete random variables this quantity is greater than or equal to 0. So I can upper bound this mutual information by uncertainty in these xi. So mutual information between u1, u2, un and x1, x2, xn can be upper bounded by entropy of x1, x2, xn. Next, we are going to use data processing lemma. We just said that u1, u2, basically ui's, xi's and ui hat, they form a Markov chain, right? So then mutual information between ui's and ui hat has to be less than mutual information between ui's and xi. This is a result which follows from data processing lemma. So we can write the mutual information between u1, u2, ul and u1 hat, u2 hat, ul hat. This from the data processing lemma follows that this is less than or equal to mutual information between u1, u2, un and x1, x2, xn. Now this quantity we have shown in the previous slide that this quantity is upper bounded by uncertainty in x1, x2, x3, xn. So we plug that in. So what we can write then is this is upper bounded by this quantity, correct? And each of these xi's are DRE random variable, right? And this is a block of length n. So there are total d raised power n possible values of x1, x2, x3, xn. And we know from the property of entropy that this is greater than or equal to 0 and less than or equal to log of number of possibilities of x. So in this case number of possibilities of x1, x2, xn is d raised to power n. So this entropy is upper bounded by log of d raised to power n, which is nothing but n log of d. So what we have shown so far is mutual information between u1, u2, ul and u1 hat, u2 hat, ul hat is less than equal to n log of d. Now, since we are considering a discrete memoryless source, so these ui's are identically distributed and they are independent. So, if they are identically distributed and independent, I can write this h of u1, u2, ul as h of u1 plus h of u2 plus h of ul, and since u1, u2, ul are identically distributed, this will be same as h of u. So, this h of u1, u2, ul can be written as h of u plus h of u, and this repeated L times. So, then this will be L times h of u. Now, from the definition of mutual information, I can write the uncertainty in ui's given ui hat to be equal to uncertainty in u1, u2, ul minus mutual information between u1, u2, ul and u1 hat, u2 hat, ul hat. Now, this quantity we know from this relation that this is equal to L of h of u. So, we plug this value here. Now, this quantity we have upper bounded by n log d. So, if we are subtracting a larger quantity, so then this would be greater than equal to LHU minus n log d. Okay. Next. So, using chain rule, we can write this h of u1, u2, u3, ul given u1 hat, u2 hat, ul hat. We can write them as u1 given u1 hat plus u2 given u1, u2 hat, like that we can write, and then we can use the property that conditioning cannot increase entropy. So, this result comes from two facts. First, we are applying chain rule. Second, we use the fact that conditioning cannot increase entropy. So, if we combine those two results, we can write uncertainty in u1, u2, ul given u1 hat, u2 hat, ul hat. This is upper bounded by h of ui given ui hat sum over all i's. Now, from Fano's lemma, we know the uncertainty in ui given ui hat, this is upper bounded by binary entropy function of error, probability of error, log of number of possibilities of this random variable u and u hat, that, and this u is a k-ary random variable, and we have shown this is given by log of L minus 1, where L in this case this is a k-ary random variable. So, in this case number of random variables, this is cardinality of ui is k. So, from Fano's lemma, if you recall, we can write u given u hat is less than equal to binary entropy function of this probability of error plus probability of error log of L minus 1, where u and u hat are L-ary random variable. In this case L is k, in our u is a k-ary random variable. So, that is why I am writing here this as k. Now, next thing what I am doing is I am summing up this over all i's. So, I am summing this over all i's. So, I sum this up over all i's. I sum this right hand side over all i's. If I do that, I get this expression. Okay. Next, I can divide this whole thing by 1 by L, right. Now, if I divide this whole thing by 1 by L, what I get here is this term is going to be 1 by L summation h of ui given u hat. This will become 1 by L summation binary entropy function of this error, and this pi log of k minus 1, this was L times, we know pi is given by 1 by L summation. If you look at what is pi, let's go back to definition of pi. Summation pi is L times ps, right. This summation pi is L times ps. So if we plug that value in here, what we get is, so when we do summation, this is L times ps log of k minus 1, and now we are dividing by 1 by L. So this will be 1 by L times this, and this will be ps log of k minus 1. Now look at this function. This is like we are calculating the expected value of a binary entropy function. Now what do we know about binary entropy function? The binary entropy function is a concave function, right. A binary entropy function, if you recall, looks like this. This will be 1 corresponding to p equal to 0.5, and this is 0 and 1. So binary entropy function looks like this. So this is a concave function, and from Jensen's inequality, what do we know? If the function is a concave function, then expected value of the function is going to be less than function of expected value of x. So since binary entropy function is a concave function of p, we invoke Jensen's inequality, which says expected value of the function is less than function evaluated at expected value. So what is the expected value of the binary entropy function? That is this quantity. And what is the function? Function is a binary entropy function evaluated at expected value of this x. Here it was pi. So this is the expected value of this pi. And what is this term? From the definition of average probability of error, this is nothing but binary entropy function of the average error. So then, combining this expression and this expression, what we get is, and of course this expression as well. So we combine these expressions. So this says uncertainty in u1, u2, ul given u hat, u1 hat, u2 hat is upper bounded by this, and from here we get another upper bound. So combine these two, we get this expression. All right. Now, what is this term? This also we have proved earlier. This is given by, if we go back and see, this term is given is lower bounded by L h of u minus n log of d. So if we use this result, what we are going to get is an expression like this. Okay, and further simplifying, we get the desired expression that we wanted to prove. So what we have shown here is the binary entropy function of this average error plus average error log of L. This is lower bounded by h of u by log d minus n by L whole multiplied by log of d. So, if you try to make this much smaller compared to this, you are going to pay a penalty in terms of your probability of error, average probability of error. So, if this becomes much smaller than this quantity, this lower bound is going to increase. So, this will increase your probability of error. So, you cannot make n by L arbitrarily small and still achieve very low average probability of error. So, then to summarize, if you the case of block to block length coding is a case of lossy source compression. We take large blocks of data and we are basically coding it into small blocks of data. The trick is you should try to encode all these typical M typical sequence using unique code words and assign one code word for all non-typical sequences. Now, since the probability of occurrence of this typical sequence is close to 1 when we are considering large block size, we will be able to correctly decode at the receiver most of the time. So, with this I will conclude my discussion on block to block length coding. Thank you.